So what we do is correlate this changing of the fluorescence with the analyte we want to detect. So, of course, we do optimization of the system, all the parameters. I'm not entering now in details how we optimize the system, but once the system is optimized, all the parameters, the quantity of the quantum dots, the antibody we use, and all these parameters, including the volume of the sample and so on, we find the system ready to work and detect E. coli. So to make the system more available for different other applications, because this previous system is very much dependent on the distance between the donor and acceptor, and in fact, in case of bacteria, it's easy to have this big distance and allowing the shining of the quantum dots. We used some beads, silicon beads, now modified with antibodies as spacers, so we achieve the same system as we had before, but mimicking a little bit the distance induced by E. coli now by these silicon beads, and in this way we are able to extend the operation of this system even for low-size analytes, for example, proteins, in addition to bacteria. So, importantly for the operation of this system in paper, we can have even a very simple device that is not even based on lateral flow, but in just a device that can operate putting directly in contact with the sample. For example, you can see here this nano paper coated with graphene oxide and some quantum dots with antibodies that stand on top. So we start from the system that is already quenched, and open interaction of this system with bacteria, for example, due to the interaction of bacteria with antibodies or some proteins with these antibodies, depending on the receptors we put here. We have a turned-on fluorescent system that responds, give a very nice response directly, no need for even washing. So we have a very simple system. I show here some results, operation of this system, either for pathogens. We have evidences of the images and microscopies for the operation with pathogens, but also for the proteins. So the system is able to work either as immunosensing platform, but also for either pathogens or proteins. So extending now these graphene-based detection systems to other analytes, for example, this is the case of pesticides. There is a lot of need to detect these small compounds listed in the very, very contaminants, dangerous contaminants in seawater. We are working with pesticides also. For example, this is the case of pesticide detection, the TBT. What we do is we start from some aminated magnetic silica beads that are modified with graphene quantum dots, and we put on top of these magnetic beads also a layer of imprinted we are using molecular imprinting polypyrrole that is used to detect this pesticide. So we have these beads with quantum dots that already have the fluorescence, and open the interaction of these magnetic beads with the analyte, we have the fluorescence turned off. So we have a very simple system, and the combination of this with the magnetic beads allows for the pre-concentration, because we can detect very low quantities of pesticides in seawater, because we immerse these beads in the water, in the sample, and then we can attract these by magnetic field. So after, of course, characterizing the system, being sure that we have all the connections, I'm not entering now in details of this. We do all the microscopy, spectroscopy, Raman, to see that all the system is working well. And as you can see here, the system is responding very nicely to very low concentration of pesticides, ranging from few ppbs to ppm levels, either in water or in seawater, which is really a very complex system with a lot of other compounds, and the system was found to be sensitive and selective. So going further with these devices, so we thought, why not to have a very simple platform, so operating with graphene quantum dots. So what we did is we put these quantum dots now into the paper and trying to see the interaction of these graphene quantum dots with different compounds. For example, some phenolic compounds, and we found that different compounds are behaving in different modes based on the pp stacking onto the graphene quantum dots. We found that a class of compounds were able to induce this quenching. And this is really very important because for contaminants detection, you don't need to find exactly what molecule is there, because in water you may have thousands of contaminants. So it's very important to find if the water is contaminated, can be used or not. So detection of family of compounds is really very important. And what we achieve with this is by simple imaging of this paper with graphene quantum dots based on the quenching of fluorescence, we are able to detect different kinds of compounds, and the idea is to convert these to family detection compounds or toxicity tests with interest for water toxicity and other applications. You can see also here how the system works, just to see how simple and how these images are taken. So we are defining first these with wax, some circles, and there we are putting graphene quantum dots. After excitation, you see that these graphene quantum dots have really a very nice photoluminescence. And after that, you'll see how this photoluminescence is quenched open interaction with different samples that contains different kind of analytes. So just to see that this is really very simple, and by measuring the change of the photoluminescence, we are able to correlate this with the analytes, the contaminants we want to detect. We build also a very simple mobile phone-based detection system where the excitation is already done there. So this is in fact a patented system, and we are looking for collaboration to use this. You see here the strip of the paper is very simply inserted, and then we detect this change of the photoluminescence by interaction with different kind of analytes. So I'm just trying to explain finally some application with patterning systems. So we have this patterning of exfoliated graphene to build different kind of electrodes by using paper membranes. So by wax patterning, we are able then to, after filtering graphene, and we can transfer this graphene oxide or graphene oxide mixed with different kind of nanomaterials to any surface. So after controlling, of course, of the performance of these devices, so we have nice reproducibility and good printing width and printing with interest for these kind of sensors. So the nice thing of this technology is that we can print any kind of material, even a mixture of graphene oxide or other 2D materials with nanoparticles, with receptors, and we can bring directly the sensing surface to any kind of material. So here, just a touch-sensitive device showing that this system is really very easy. So we can, here, I am not able to move this. Anyway, so it was a video showing this turning on off of this device. As I said before, we can pattern to any kind of surface, textiles, plastic, paper, adhesive films, and we are trying to work and build wearable devices with this. So this is an example of enzymatic sensor working with tyrosinase enzyme, which is well known for phenolic compounds detection, and this operates through the formation of ketones and the reduction of ketones onto the surface of the electrode in the case of the detection, for example, of phenolic compounds in water. What we found after, of course, controlling of the graphene we are using, so very important to see the grade of oxidation, and after controlling this grade of oxidation of the graphene we're using, we found out that the sensor was responding really very nicely. You can see here the response of the system toward the increasing concentration of phenolic compounds. This is the case of the sensor without graphene, and you see here the sensor with graphene oxide, and then with less oxide, so more reduced, who is responding better. So the effect of graphene is evident, so we have a better sensitivity response in the case of graphene. We also found some interesting application, for example, to detect some volatile compounds with interest for gases. We are still not able to do this selective, but we are thinking on using some receptors and trying to do some modification of graphene to do detection of some gases with interest for. And finally, in 1 minute, probably 2 minutes, we are also trying to use graphene in some other interesting application. For example, removal of contaminants by using graphene oxide-based chips. After building some chips and doing some immunodetection inside, we use an extra part of the chip with graphene oxide to remove the contaminant. In this case, this is polybrominated diphenyl ether, which is highly reported as a contaminant. So the system is able to do the detection of this contaminant, and then the graphene oxide is removing the contaminant. So it's a kind of smart chip that is doing detection, but also at the same time removing the contaminant. So avoiding the release of the contaminants out of the system. Or the detection the same way of heavy metals. So we have these very nice PDMS-based chips modified with graphene oxide and use these to detect heavy metals. So in the same way, so this is really very interesting because sometimes we are involved in developing biosensors, but we are not thinking about the contaminants that we are probably using during this detection, and we should take care about that. So this is really very important. And finally, there is an example of motors we are also trying to build. This is from a project we have been collaborating with Professor Joseph Wang in the United States. So these are simple devices produced by electroplating, and we have been working with this in collaboration with Dr. Wang and trying to use these, for example, to detect the bacteria, to detect other compounds. So these devices are electrocatalytic, so we are trying to use these, for example, and you can see here how these are operating. So by releasing oxygen as is used as a propulsing force, these devices can move, and in fact, they can catch any kind of analyte. For example, you can see here they are catching bacteria in different kind of samples, and even in the presence of other compounds or other bacteria. For example, E. coli in presence of Cerevisiae. So the system is really very selective. We thought, why not to use also graphene and see some nice applications, and in fact, we used silicon beads modified with reduced graphene as Janus micromotors. They contain also platinum for catalytic purposes, and we use these devices to remove some contaminants, and you can see here the efficiency of movement and removal of these by using this kind of devices. So let me see here, there is a video. So just to see the differences in the case of the motor and the release, the change of the concentration of this compound after removing by this device. And finally, a device that is now produced by graphene. So we thought, why to use this technology and not a very simple one? So we stamp now the motors by using this stamping of graphene. So, and this is really very interesting. So we are preparing this wax printed membrane. We filter graphene on top of this, and after that we release this graphene after putting this in contact with ethanol. So we are trying to study the scrolling direction, and in fact we found out that there are nice shapes depending on the way how we scroll these devices, and controlling the scrolling direction we are getting different kind of device. So this is the first time that we have a whole graphene-based motor. And just to see here that these are working, so based on the propulsing of this oxygen, so you can see the movement of these in different media. We don't know still what to do with these devices, but the nice thing is that we are able, just by stamping of graphene, to end up with these devices that we are thinking probably to connect with receptors and use these to do some operations. So the final device, an electroluminescent device, is also reported where we transform this electroluminescent device to a sensor to detect either different gases, but also with interest for breath capacity measurement. So this is the end. I think I can... Finally, I want to conclude. I hope that I convinced you that there are some interesting applications of graphene in biosensing field for diagnostics, safety, security, environmental monitoring. So I would like to say that you also can see this in different review papers we have written. So if you want, and thanks to all the collaborators who have done this work. These collaborators already left the laboratory, are working in different places, and of course I would like to thank my current collaborators and all you for your attention. Thank you very much.
Thank you, Arben. Very interesting overview. Can you comment on the capacity of graphene oxide to quench quantum dots? Does this depend on the type of quantum dots, functionalization, concentration, type of solvents?
Depend on the kind of quantum dots you are using. So, in fact, we have been working with some cadmium selenide quantum dots of around 2 nanometer size. In our case, we have these quantum dots modified antibodies. Imagine that the kind of receptor you are putting, and of course the size is very important, because this quenching will depend on the distance between the quantum dot and the graphene. So whatever you put in between will affect the distance between these two. So this is very much depending on that. So
I was wondering how effective is this paper quenching, and then you show that adding the GO, you completely quench the spot.
Yeah. So this work really very nice. So the graphene oxide is quenching, and the efficiency of this quenching, the quantity of this, depend, of course, on the quantity of the analyte you are using. So more analyte you have or less analyte you have, the quenching will be different. So we are able to quantify this change. So.
Okay, thank you.
Any other question?
Very interesting presentation. One question about the contaminant removal. As far as I got it, this was an add-on to the chip. So what quantities of contaminated water could you purify with this chip?
Yeah, this is just to understand. So the chip, the main objective of the chip is to do the detection. So we are detecting this analyte in the water. So the idea is not to do decontamination. We are just removing what we are using in this chip. So it's a kind of decontamination during the detection system, detection process, not for industrial purposes. Yeah.
Okay, I see.
Maybe I can finish with a quick question. So the sensor that you have for bacteria right now are on-off switch?
In case of optical
yes,
detection.
E. coli detection.
Yeah.
So would it be possible to make it specific for bacteria so that you can do like to know what type of bacteria is in
of course,
there?
this system is also specific because we connect these quantum dots with antibodies against the specific bacteria. So if we change the antibody or use a kind of array of, we can put different antibodies and we can convert these to a system that can give on-off, but for different bacteria, changing the antibody.
So for the sake of time, thank you again.
Thank you very much.
So our next speaker is